In this problem, we're given 3 points, 0, 1, 1, 1, and 2, 3, and we want to use Lagrange interpolation to construct a degree 2 polynomial through these 3 points. So the Lagrange interpolation formula for 3 points is p of x is equal to y0 times delta 0 of x plus y1 times delta 1 of x plus y2 times delta 2 of x. So here, y0 is 1, y1 is also 1, and y2 is 3. Delta 0 is going to be given by x minus x1 times x minus x2 all over x0 minus x1 times x0 minus x2. Plugging in numbers for x1 and x2 and x0 gives us x minus 1 times x minus 2 all over 0 minus 1 times 0 minus 2. Simplifying this expression will give us 1/2 x squared minus 3/2 x plus 1. Similarly, we have for delta 1, x minus x0 times x minus x2 all over x1 minus x0 times x1 minus x2. Plugging in numbers again will give us x minus 0 times x minus 2 all over 1 minus 0 times 1 minus 2. Simplifying this will give us minus x squared plus 2x. Finally, for delta 2, we have x minus x0 times x minus x1 all over x2 minus x0 times x2 minus x1. Plugging in numbers one last time gives us x minus 0 times x minus 1 all over 2 minus 0 times 2 minus 1. And simplifying this will give us 1/2 x squared minus 1/2 x. So now we just plug in the delta 0, delta 1, delta 2 into the above formula to give us the Lagrange interpolating polynomial. So here, y0 is 1 times delta 0, which is 1/2 x squared minus 3/2 x plus 1, plus y1, which is also 1, times negative x squared plus 2x, and that's it, plus y2, which is 3, times 1/2 x squared minus 1/2 x. Now we simplify this expression to get our final answer, x squared minus x plus 1. Now we can get a little more intuition in this problem if we plot the delta 0, delta 1, and delta 2. So we know that delta 0 has a root at 1 and 2. And we also know that plugging in 0 for x will give us 1. So we can plot those 3 points. So then we get a quadratic that looks something like this. Similarly, we know that x or delta 1 has roots at 0 and 2. And plugging in 1 for x will give us 1. So the quadratic looks like this. And finally, For delta 2, we have roots at 0 and 1, and plugging in 2 will give us 1. So the quadratic looks like this. So we also scale each of the deltas up by their respective y's. So delta 0 will be scaled up by a y of 1, delta 1 will be scaled up by 1, and delta 2 will be scaled up by 3. So the only real work that we have to do now is scaling up delta 2, because all the other ones are scaled up by 1. So scaling up delta 2 will still give us roots at 0 and 1, but then delta 2 at x equals 2 will give us 3. So this point here goes up here. So now adding these three polynomials together will give us a point here, a point here, and a point here, which are exactly the 3 points required in the problem. In this problem, we're given 4 points, the first 3 of which are the same as in the previous problem, and the fourth point is negative 1, 3. The question asks, does there exist a degree 2 polynomial through these 4 points? So the first step is to make a picture. So the first point, 0, 1, is here, 1, 1, 2, 3, and negative 1, 3. So in the previous problem, we found a polynomial that passes through the first 3 points. And it looks something like this. So now, let's try and see if our previous polynomial, whose equation is given by x squared minus x plus 1, passes through this fourth point here. So to do that, we simply need to evaluate p at negative 1. And we see that p of negative 1 is 3. So it indeed passes through this fourth point. So our answer is yes. And the previous polynomial works. Again, we are given 4 points, the first 3 of which are the same 3 points in part 1.1. And our fourth point is negative 1, 0. So let's start with the picture again. We have the points 0, 1, 1, 1, and 2, 3. And also negative 1, 0. So immediately from this picture, we should see that there doesn't exist a quadratic through these 4 points. So let's try and prove this formally. Suppose for the purposes of contradiction that there exists a degree 2 polynomial, call it p of x, that passes through the above 4 points. Now in particular, p of x must pass through the first 3 points. And in part 1.1, we showed that p of x equals x squared minus x plus 1 works. Now we also know that the Lagrange interpolating polynomial is unique. So this is our only candidate polynomial for passing through the first 3 points. So all we need to do is verify that it passes through negative 1, 0. So plugging in negative 1 gives us three, which is not equal to 0. Thus, p doesn't pass through negative 1, 0, which contradicts our original hypothesis. We know from the previous part that if there exists a polynomial of degree at most 2 that passes through these 4 points, in particular, it must pass through the first 3. So we can construct via Lagrange interpolation a degree 2 polynomial P2 of x that passes through x1, y1, x2, y2, and x3, y3. And we know that this polynomial is unique. So all we need to do is verify if P2 of x4 is equal to y4. If this is true, then our answer is just P2. Else, we return false.